All right, so this part we are going to discuss gas laws. Um, in the previous video, I think you have an idea what we are talking about when we talk about gas laws. Um, Now, what is important at this point is for you uh, to read the statements that are given here. These statements show the laws that we are going to deal with in this video. So we have Boyle's law. That's how it is represented mathematically. We have Charles' law, mathematical representation. We have combined gas law. Its representation is given here. Then we have Amonton, how it is represented, Avogadro's, and how it is represented. So when we think about all these gas laws, we explain them using a theory that we call kinetic molecular theory of gases. So that is the theory that helps explain all these gas laws. Now, what are the gas laws? The first law we are going to talk about is called Boyle's law. So this law says that for a fixed amount of gas, so for a specific mass of gas at constant temperature, so we have fixed mass and we have constant temperature, pressure is inversely proportional to volume. So in simple terms, you want to show that pressure, which is P, is inversely proportional to volume. What it means is that as you increase pressure, the volume drops. So we can say pressure goes up, the volume goes down. And think about what is constant in this case. So the constants we have, the first one is the mass of gas, mass or the moles of gas. So these are constant. The second constant we have is pressure, because we are saying not pressure as such, but temperature. Because we are saying this is happening for a fixed mass at constant temperature. So temperature. So if I can change. So here we are showing that P is proportional to 1 over V. If we want to get rid of this proportionality sign and use an equals sign, we need to have a constant. So we can show that P is equal to a constant here divided by V, where V is the volume. Or if we multiply both sides by V, so we cancel here, we have PV is equal to a constant. Now that is the Boyle's law, or the statement of the Boyle's law. Normally, when we discuss these laws, we think about two systems. So if I draw this law for two systems, each system has its own pressure and volume. I will show that P1 V1 is equal to P2 V2 because both of them have the same answer, and this answer is a constant, which is K. So I can say P1 V1 is equal to P2 V2, which is equal to K. But usually we don't include K at this point. So I can get rid of the K there. And this is what we call Boyle's law. Now we want to look at a calculation that we can do using this Boyle's law. So in your calculation, what you want to look for is, are you given P1? Are you given V1? What about P2? What about V2? That's what you are looking for as you are solving Boyle's law problem. So here is our problem. A person has an initial lung volume of 2.75 liter. So immediately we know that this one is our V1, which is filled with air at an atmospheric pressure of 1.02 atmospheres. So this one is our pressure 1. If she increases her lung volume to 3.25 liters, now this is our V2. Without inhaling any additional air, what is the pressure of her lungs? So this one is our P2. Now this is what we want to determine. So for this one, we just go on and say P1 V1 is equal to P2 V2. That's what we are looking for. But our aim is to obtain P2. So how do we do that? The way I have written this problem or this equation, I can as well say P2 V2 is equal to P1 V1. It's the same. Now I want to isolate P2 to be on its own. For that, I will divide both sides by V2 so that the V2 cancels this side. Then I am going to have P2 is equal to P1 V1 divided by V2. So let me just get rid of this one. So P2 is equal to P1 V1 divided by V2. Now I'll just slot in the values. So the P1 is 1.02 atmosphere. The V1 is 2.75 liters divided by the V2 is 3.25 0.25 liters. So when you divide that, you get your answer to three significant figures, 863 atmospheres. So here it makes sense because we are calculating pressure, final pressure, or P2, which should be given in the units of atmospheres. So that's the Boyle's law calculation. Then we have a second law that we call Charles' law. So, this law really focuses on volume and temperature. Like what happens to gas if you increase its temperature or if you decrease its temperature. So the law says for a fixed mass of gas, so we also have a fixed mass here, but at this point we have constant pressure. Temperature is directly proportional to volume, and we need to take note that the temperature is given in Kelvin, K. So here we say V is proportional to T. Now, if we want to remove the proportionality sign here, we can say V is equal to KT, where K is just a constant. Or we can say V over T is equal to K. That is, if you divide both sides by T. So if you divide here by T, divide here by T. So these T's cancel each other, and we have V over T is equal to K. And that is Charles' law. So I just write this K again. Now, this law for two systems, if you are showing it for two systems, you can say V1 over T1 is equal to V2 over T2. Both of them are equal to K. But usually for two systems, we don't include K. So I can just delete this K here. Now, let's look at a problem that we can solve using this Charles' law. Here we have a sample of gas that has a volume of 2.80. So immediately, this is our V1. At an unknown temperature, this unknown temperature is T1. When the sample is submerged in ice at T is equal to 0.00 degrees Celsius. So this is T2. But remember, you need to give your temperatures in Kelvin. So we need to change T2 into Kelvin to solve this problem. Never use degrees Celsius when solving gas laws problems. So in this case, T2 will be equal to 0.00 plus 273 Kelvin, which is equal to 273 K. So that is T2 coming from here. So what I've done is to change the temperature from degrees Celsius to Kelvin. Its volume decreases to 2.57 liters. So this is V2. What is its initial temperature? So here we are finding this T1. So how do we solve this problem? Here, following the Charles law, we say V1 T1 is equal to V2 T2. That's what we are solving here. But this can be inverted. This can be inverted. So what do we say is we can have T1 over V1 is equal to T2 over V2. So both of them are correct. So we want T1. So what we need to do is to multiply both sides by V1 so that we cancel out the V1 on the left side. So this will cancel with this one. So in the end, we go all the way to here. In the end, we have T1 is equal to T2 V1 over V2. Then we just slot in the values. So our T2 is 273 Kelvin. The V1 is 2.80 liters. The V2 is 2.57 liters. So this calculation gives us a T1 of 297 Kelvin. Now, if you want, you can change this Kelvin to degrees Celsius. So degrees Celsius is equal to 297 minus 273. So for that, we get our temperature in degrees Celsius as 24 degrees Celsius. So a problem like this one, you can leave your answer in Kelvin, or you can convert back from Kelvin to degrees Celsius. But if you are solving the problem, make sure that you are always using Kelvin in the problems. Let's look at another problem based on Charles' law. So we have a gas in a cylinder with a movable piston which has an initial volume of 88.20 milliliters. So this one is our V1. If we heat the gas from 35 degrees Celsius, so immediately you need to change 35 degrees Celsius Kelvin. So 35 degrees Celsius is 308 Kelvin. To 155 degrees Celsius, this one is 428 Kelvin, because we always want to use Kelvin. This is T1, this is T2. So we have V1, T1, and T2. So the question is, what is the final volume? So this is what we are looking for, V2. So as usual, Charles' law says V1 T1 is equal to V2 T2. And we want T2 to be on its own. Or we want V2, that is, we want V2 to be on its own. So what we want to do is multiply both sides by T2 so that V2 can be on itself. This cancels here. We remain with V2 is equal to T2V1 divided by T1. So we will say V2 is equal to 88.20 milliliters times 428 Kelvin, that is the temperature, divided by 308 Kelvin. That's the T1. So for this, our answer is 123 milliliters. So our answer is 123 milliliters. Actually, I will change this one to 3 significant figures so that I have my answer to 3 significant figures. So 35.0 degrees Celsius. So our answer will be to 3 significant figures, in this case 123 milliliters. That's how we solve Charles' law problems. We can combine Charles' law and Boyle's law and make them a single law that we call combined gas law, or combined Boyle's and Charles gas law. So let's look at Boyle's law. Boyle says PV is equal to constant. Charles says V over T is equal to constant. So we are saying if we add the two laws, we'll have PV over T is equal to K. So this part, the PV is equal to K, is Boyle's law. So let me see if if I can erase this part. So this part, the P and V, is Boyle's part, Boyle's law. While this part, the V and T, Charles' law. So when you add the two, you have your combined gas law. So we are going to say combined gas law, P V over T is equal to the constant. Now for two systems, we are going to say P1 V1 over T1 is equal to P2 V2 over T2. So that is the statement of the combined gas law. So it's combined because we have Boyle's law and Charles' law to make a single law. Let us see what problem we can solve using the combined gas law. If I initially have a gas at a pressure of 12 atmospheres, so this is my P1, a volume of 23 liters, this is my V1, and a temperature of 200 Kelvin, this is my T1. And then I raise the pressure to 14 atmospheres. So this one is my P2. And increase the temperature to 300 Kelvin. This T2. What is the new volume of the gas? So this is what I want to find. V2. That's what I want to find. So how do I go about it? I am going to say P1 V1 over T1 is equal to P2 V2 over T2. But here I am interested in determining the V2. So what do? I want to isolate V2 from this problem. So what I'm going to do is, first I'm going to multiply this by T2 so that I get rid of the T2 down there, and do the same thing this side. T2. So this T2 will cancel with this one. So I am going to remain with P2 V2 is equal to P1 V1 T2 divided by T1. Then I'll have to get rid of this P2 here by dividing both sides. So whatever you do on one side, you need to do exactly the same on the other side. If I divide by P2 on the left side, I need to divide by P2 on the right side. If I multiply by T2 on the right side, I need to multiply by T2 on the left side. So here, the P2s will cancel this side. Then my equation V2 is equal to P1 V1 T2 divided by T1 P2. After that, I just slot in the values. So P1 is 12 atmospheres, V1 is 23 liters. T2 is 300 Kelvin. T1 is 200 Kelvin. And P2 is 14 atmospheres. So my answer will be given in liters because the atmosphere here cancels the atmosphere. The Kelvin cancels with this Kelvin. And to one significant figure, my answer is 30 liters. So that is my volume. All right, so let's look at another problem. A problem similar to this using the combined Boyle's and Charles law calculation. We have a gas that has a volume of 28 liters. So this is our V1. A temperature of 45 degrees Celsius. Now here, you are given this temperature in degrees Celsius. You need to change it to Kelvin. So this one is, which is T1, 315 Kelvin. So what I've done is 45 plus 273. Let me see if it makes sense. 45 plus 273 is 318 Kelvin, not 315. So 318 Kelvin. So we have a gas that has a volume of 28 liters, and that volume is T1 at a temperature of 318 Kelvin, and an unknown pressure. So this unknown pressure here is P1 because it is before the change. Has its volume increased to 34 liters? So the 34 liters here is V2, and its temperature decreased to 35 degrees Celsius. So this temperature here, you need to change it to Kelvin. So this is 308 Kelvin. So T2 is equal to 308 Kelvin because that is 35 plus 273 Kelvin, which is 308 Kelvin. If I measure the pressure after the change to be 2 atmospheres, so this pressure here is P2. What was the original pressure of the gas? So really, what we want to determine here is P1. So for this problem, I will say P1 V1 over T1 is equal to P2 V2 over T2. If I play around with this problem, I'm gonna multiply this side by T1, multiply this side by T1. So the T1 here cancels with this one. I will have P1 V1 is P2 V2 T1 over T2. But I want only P1, so I'll divide both sides by V1. I want only P1, so I divide both sides by V1 so that I have P1 is equal to P2 V2 T1 T2 over V1. Then I'll just slot in the values. P1 is equal to, so the P2 is 2.0 atmospheres. V2 is 34 liters. T1 is 318 Kelvin. T2 is 308 K, and V1 is 28 liters. So if we make our calculation, 2 times 34 times 318 divided by 308, we find that the answer here is 2.5 atmosphere. That is to two significant figures. That is our our initial pressure, P1. So there are also two laws that I'm not gonna spend much time on. Hamilton law, which says for a fixed mass of gas at constant volume, pressure is directly proportional to temperature. So because I have shown you how to solve calculations using these gas laws, you are going to use the same methods that I have used to determine calculations using Hamilton law. So this one is P1 over T1 is equal to P2 over T2. This deals with volume, it deals with pressure and temperature. And the constant, it has constant volume, that's one, and it has a fixed mass. That is Hamilton law. Then we have another law, Avogadro's law. This is amongst the laws that we have discussed. Avogadro's law is the one that changes the number of moles. So Avogadro's law changes the number of moles. It's the only law that you see an increase in the number of moles, which means it is the law. So only gas law so far that changes number of moles. Therefore, it also changes mass. So in an exam, if I say which of the gas laws has a change in mass, the answer is it is Avogadro's law. Which of the gas laws has a change in number of moles? The answer is it is Avogadro's law. So this is the mathematical representation of the Avogadro's law. So you need to learn these laws because these two laws, Hamilton and the Avogadro's law, because we are going to use them in the calculations that you are going to have. All right. Now, when you combine all these laws that we have discussed, you can come up with the final law that we call an ideal gas law. So this law, I'll just briefly talk about how it comes into being. So let's say we have a combined gas law here. So we know that the combined gas law is given by Boyle and Charles' law. This one is P V over T is equal to K. And then we have Avogadro's law. So we have Avogadro's law here, which says V over N is equal to K. So if we combine these two laws, we are going to have PV NT is equal to K. Or we can say PV is equal to N K T. So we are saying this K is a constant. So the K is a constant. For this one, replace K with R. We are going to have PV is equal to nRT. This one is known as ideal gas law. R is called universal gas constant. I mean, it has a range of values that you can use depending on the measurement. I mean, the value is the same, but depending on what type of measurements you are doing, the value can be given in different ways. For this topic, the value of R is 0.0821 liter atmosphere Kelvin mole. So we need to take note of this value of R. Actually, it will be given to you in an exam. But what is important is this law. You gotta have to know this law. PV is nRT. P is pressure, V is volume, N is the number of moles. So N is number of moles, and T is temperature. Temperature is always given in Kelvin. Let's see how we can solve problems using this law. So calculate the 1 number of moles, 2 mass in grams for a 14.5 liters of oxygen gas at 298 Kelvin and 2.5 atmospheres. Here you are given the R. So to solve this problem, let me just draw a line here. You are going to say from the ideal gas law, PV is nRT. So what are you given? Here, you want to determine the number of moles. You want to determine N. So you can play around with this formula and then say N is equal to PV over RT. That's what you are doing. And then you just put in the numbers. What is the P? The pressure is given here, 2.5 atmosphere. What about the V? What is the volume? The volume is given here, 14.5 liters. What about R? R is given 0.0821 liter atmosphere Kelvin mole. What about temperature? Temperature is given here 298 Kelvin. And what are the number of moles that we are calculating here? So the number of moles to two significant figures is 1.5 mole. So in the actual calculation, because I'm going to use that information to do another calculation, times 14.5 divided by 0.0821 divided by 298. So in the actual calculation, the answer is 1.482 mole. So that is the answer in the actual calculation. But our answer to two significant figures, so I would say 2SF. So our answer to two significant figures is 1.5 mole. But from the calculation, our answer is 1.482 mole. But this is your answer for this problem here. So the second part is, so this is part 1. Part 2, determine the mass in grams. Now you already have the moles. For this one, the conversion factor is 1 mole is equal to 1 mole oxygen is equal to 32 grams of oxygen, because each oxygen has a molar mass of 16. So two of them have a molar mass of 32 grams. So here you are given the moles. You just say 1.482 mole of oxygen times, from the conversion factor, down here we are going to have more oxygen, up here we are going to have grams oxygen, because we are moving from moles of oxygen to grams of oxygen. So up here we just put 32, here 1, based on the conversion factor. And from that we see that our mass is 47.4 grams. So that is the mass of oxygen. So this is how we solve this problem. So I want you to try and solve this next problem. It is exactly similar to the problem that we have solved previously. Now let me solve the last problems for this part. Let me solve this for this video, this last problem, and then we'll continue on another video. Using the equation PV is nRT, calculate the volume for 1 mole of any gas at 1.00 atmospheres for two temperatures. Temperature 1, 0 degrees Celsius, which is 273 Kelvin. And then temperature 2, 25 degrees Celsius, which is 298 Kelvin. So let us start at 0 degrees Celsius, which is 273 Kelvin. So for this one, we want to determine volume. So we are going to use the ideal gas equation. PV is nRT. Therefore, V is nRT over P. Now, N, which is number of moles, we are given that it is 1 mole. R, it is 0.0821 liter atmosphere, Kelvin mole. Temperature is 273 Kelvin. And the pressure is 1 atmosphere. Now, if you make this calculation, you find that the answer is 22.4 liter. This answer is known as molar volume at standard temperature and pressure. That is STP. At STP, the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. So I want you to do the same for 25 degrees Celsius, which is 298. When you get your answer will be known as room temperature and pressure, RTP, room temperature and pressure. So we stop here for this video. We have some more problems that we are going to solve based on the gas laws. Thank you.